Hello, this is FlippedHarber for Physics, and in this video we'll cover the practice problems on page 89, numbers 1 through 5. Now, in these problems, they all have the same common instructions. It says for each of the following situations, specify the system and draw a motion diagram and a free body diagram. Label all forces with their agents, that is what's causing the force, and indicate the direction and acceleration of the net force. Draw vectors of the appropriate length. So, number one, a flower pot falls freely from a windowsill. So my motion diagram should show my flower pot speeding up because its velocity is increasing as it goes down. So you can also see that I've drawn in the acceleration. The acceleration for this flower pot is actually equal to a number that you're going to get to know very, very well, 9.80. Now, over on our free body diagram on the right, there's only one force that's acting on this flower pot. That is the force of gravity. Now, we'll be talking about how to find that force later, but we know that there is this force called gravity that's pulling the flower pot down. The agent of that force, that is the object that's causing it, is the Earth. Number two says a skydiver falls downward through the air at a constant velocity. So my motion diagram over on the left, the skydivers are spaced apart evenly because their velocities are all the same. That's because our acceleration is zero. Constant velocity means acceleration is zero. Well, how is that possible? How does a skydiver have zero acceleration? Well, that means that the force pulling the skydiver down from gravity, again the agent for that is the Earth causes this downward force, is being totally balanced out by air resistance. So because the two forces are equal, and I've tried to show that with the arrows, the net force acting on this skydiver is zero. Whenever your acceleration equals zero, your net force equals zero. Number three, a cable pulls a crate at a constant speed across a horizontal surface. The surface provides a force that resists the crate's motion. We'll talk about that force a little bit. Now, my motion diagram, again, the crates are evenly spaced out because it's an equal velocity all the way across. The acceleration is zero. Our free body diagram, we have the crate, and there are basically four forces acting on this crate. There's the cable pulling, and I've got that going to the right. There's a resistance force from the table. Now really that resistance force is friction, and those two forces need to be equal in order for the acceleration to be zero. So I've tried to show that with the arrows being the same length. Now there's two additional forces. There's basically a force that you almost always draw in, gravity. And then because this crate is sliding across a horizontal surface, which I guess I've assumed is a table, should probably be a floor, there's this normal force, this upward force from the table or from the floor that holds the crate up. It basically resists gravity. And again, the normal force and gravity equal each other out. So our net force acting on this crate is zero. Whenever your acceleration is zero, your net force is zero. Number four, a rope lifts a bucket at a constant speed. My motion diagram, the buckets are evenly spaced, acceleration is zero. The two forces acting on this bucket are gravity from the Earth, and there's a force that we refer to as tension. Whenever you talk about the force from a rope, we label that as tension, and a lot of times we just use a capital T for that. Now we're ignoring air resistance because this bucket's probably not traveling very fast, so those are the only two forces that are acting on the bucket. They add up to a big old fat zero. Again, our net force is zero, and we know that right away because our acceleration is zero. Now, next question, a rope lowers a bucket at a constant speed. It doesn't look any different. Again, the velocities are all the same. The bucket is moving down at a constant velocity. The acceleration is the same. It's the same two forces, and again, they add up to a big old fat zero. Whenever you've got constant speed or constant velocity, your net force is zero. Okay, so there's some examples on drawing free body diagrams. It's time to get to work. I'll see you in class, and I'll see you online.